Our next example of two wheels that are fixed with the same center is here. I have radius number 1 is 10.1, so that's the larger outside wheel. Radius number 2 is 8.3 centimeters, that's the smaller inside wheel. This is the reverse of what we had before. Don't always assume that wheel 1 is the larger or the smaller. It's whatever you're given in the problem. And we're given, so what happens is, as this larger wheel looks like we're rotating, I always put my arrows in. I learned that in physics way back when. And so as here, we're rotating clockwise. So this is feeding in and the belt is feeding out. And as that does, the smaller wheel has this wrapping around. And so we're lifting this weight out of a well or a pit or something. And so as a certain amount of wheel chain feeds into this larger outside wheel, that will cause this to rotate, that will cause this to lift, and a certain amount of chain will be lifted up and will lift this weight a certain distance. So it says here that if 33 centimeters feeds into W1, the large outside wheel, how much will feed into, or if it were on the other side, out of, doesn't matter, how much feeds into wheel number 2. Remember that the chain or the belt or the rope or whatever the substance this is, however much feeds in or feeds out, that's the arc length. And so in this case, the centers are fixed, and so the angles are the same, the thetas are the same. Theta 1 and theta 2 are always going to be equal here. We're given arc length of the outside wheel. We want to find the arc length of the inside wheel. And so let's write out our basic analysis. Every time you have this basic analysis written out, if you want to get full credit out of me, you will write this out. And don't put it all over the place. Put it right here, and then put the values here, and then scratch work over here to the side. That way you know what you're doing, you can keep track of yourself, and I can keep track of what you're doing. And believe me, when you go to some physics course or a mechanics course, they're going to appreciate that you're actually showing your work in a neat fashion. So, what do we have? We're given the arc length of wheel number 1, right? 33 centimeters feeds into wheel number 1. So we're given the arc length of wheel number 1. So we're given arc length, make that S number 1, from which we can compute, because all the radii are given, from which we can compute angle number 1. But angle number 1 is the same as angle number 2, from which we can compute arc length number 2, and arc length number 2 is what we're asked to find. So this is our structure. Follow this, write this out so you don't get lost in the process. So that's my structure. Now the actual values. So S1 is given, that was given to be 33 centimeters. And I guess I'll make the physics people happy. There we go, 33 centimeters. From that, we should be able to compute theta 1 in radians. And how do we know that? Well, we know that S equals R theta. So we know S1 is equal to R1 theta 1. And so S1 is given to be 33. Just plug and chug now. Radius 1 is known somewhere. Radius 1 is known to be 10.1 times theta 1. Oh, of course, what's happened is you've already turned the video off and worked it by yourself. If you haven't, turn the video off now. Pause the video and see if you can work this the rest of the way out, just to be sure. And then when you come back in, we'll make sure that I'm matching your work to make sure I did it right. Okay, so let's see. So theta 1, divide both sides here. So this is 33 divided by the 10.1 is theta 1. And let's see, now after you have represented what you're doing, after the algebra, then you go to the calculator computation, not before. So I have now, I'm going to clear, I'm going to say 33, I'm going to divide it by my 10.1, and I have 3.267 something. So that's my 3.267, so on, is theta number 1. And since I've not done this before, I'm going to double check my work. 33 divided by 10.1, I have 3.2673, and so on and so on. So this is 3.267. 267, so on, so on. Leave those decimals in the calculator. From theta 1, where are we? Where are we? So check, we got that. Check, we got that. Now theta 2, but theta 2 is equal to theta 1. So this is the same thing as theta 2, which is 3.267. Leave those numbers in the calculator. And then the last piece is we're going to find S number 2, because we know S2 is equal to R2 theta 2. All right? Some people prefer to represent the angle, instead of using theta, they prefer D. If you prefer R2 D2, that's fine by me. Okay, so S2 is given. Let's see, S2. Oh, that's what we're looking for. R2 is given. Where's R2? R2 is 8.3. And theta 2 is the number we just found. It's the number still in the calculator. 3.26, so on, so on. And so if I multiply the number in the calculator, just say times at 8.3. And my number is 27.1188. And so on. Let me double check that just to be sure. So that's my number. And I'm going to take that times 8.3. I'm going to double check my computation. 271188. That's good. And let's see. So that is 27.1188 on yan. And we want to round to one decimal place. So this 1 means this stays the same. So we will use S2 equal to 27.1. And again, just to keep the physics people happy, what is this? The units are centimeters. And there we have it. Now, potentially, and this is what we'll do on the next example, potentially this could be attached to another wheel, another gear. You could have an entire gearing system here. That's the whole nature behind power transfer and mechanical advantage and how machine tools work. And so the basis of this computation is fundamental to the kinds of works that certain types of engineers will be doing on a regular basis. Much of it's automated, but this is the guts of it behind the scenes, and this is the basic structure, the old school basic structure of how things actually work.